All right, so now we're going to try to do the impossible. We're going to try to do all of calculus in under 20 minutes. So we have to act really, really fast, go through the whole course. Let's begin. The first two basic issues of calculus, two big questions. What are they? How do you find instantaneous rate of change? How do you find how things are changing instantly? And then, completely separate from that, how do you find areas under curves? Two completely different questions. Turns out answers are completely related. Let's see how they go. Question one, instantaneous rate of change. What are we going to do? Well, what you do there is you first remember, what does rate mean? Well, rate is just change in distance over change in time. It's as easy as that. Distance equals rate times time. Not a big deal. Okay, now what do you do with that? Well, if you graph a function that represents sort of distance against time, then what do you notice? If you want to look at the change in time and the change in distance, what do you got? You actually got a slope of a line. Right? This is slope, rise over run, change in distance over change in time, distance over time. So you got a slope. So automatically we see a really neat thing. We see that the average rate of change between 2 points is equal to the slope of the line connecting them. Well, that's really cool. By the way, what about lines? Maybe you forgot about lines. Well, let me remind you about lines. Okay, no problem. We can do lines. We can do lines. Lines, y minus y1 equals m times x minus x1. This is the point slope form. All you need to give me is a point on the line, x1, y1, and a slope, m. You give me those two pieces of information, I can always write down the line uniquely. Always, always, always. Never forget it. Okay, fine. So now we're back to here. Now we can find average rate, and what do we see? Well, in fact, a line that touches the curve at 2 points is sometimes called a secant line. So in fact, we just discovered that the average rate, change in distance over change in time, is equal to the slope of the secant line. Cool. So all you have to do, you want to find average rate, connect the 2 points with a line, find the slope, you got the average rate. No biggie. But that's not what we want. We want instantaneous rate. So how do you do that? Well, what would that be? Well, if I want to find instantaneous rate here, what would I do? I'd make that secant line closer and closer and closer, bring these points together, and look what I'm converging to. I'm coming to a tangent line. Wow. Instantaneous rate of change equals the slope of the tangent line. So what we want is slope of tangent line. Well, what's the slope of the tangent line? It's change in y over change in x, change in distance over change in time. But now the change in time from that point to itself is 0. 0 over 0. So I'm getting 0 over 0, which is complete garbage. And that is a big problem. Our first major problem of the course. Okay, so what do? Well, we can that. Distance equals rate times time. We're going to can that. Instantaneous rate of change, I really want that. So what do? Well, how do we get that 0 over 0 problem to go away? The answer is we inch up to it. We just approach the 0 point. And what would that look like? Well, let me remind you what you've done when you were a little teeny kid. When you were a little teeny kid, this is what you were looking at. You were looking at a value of function at a point. Value of function at a point. Okay, not a big deal. There it is. F of a, it's that point. But you don't know anything else about the function. You don't know what's going around there, because all you're looking at is f of a. You open it up, woohoo, the function will be quite interesting. Who knows? Okay, but now what I invite us to do, and what calculus invites us to do, is to look at the function this way. Cover up that point and look at everything else. Open the window, look outside. That's where calculus is. And what you see here is we can see what things are approaching, and we can actually determine the idea of a limit. The limit is what things are approaching. We don't care about what actually happens at that point, only what things are approaching. Armed with the idea of a limit, what can we do? Well, now we can return to the question and figure out, let's take the limit as delta t goes to 0. What do we get? We get 0 over 0. That is called an indeterminate form when you get 0 over 0. So what do? You've got to do some algebraic gymnastics. You can either factor the top and cancel with the bottom. You can try to multiply by the conjugate. You can try to combine the fractions. There's all these tricks into the trade to actually reduce this to something that you can actually find. So you find the limit. Okay, well, once you find the limit and you take the limit as delta t goes to 0, what do you get? You get the answer to the question, how do you find instantaneous rate of change? The answer is what we call the derivative. And what's the derivative? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Looks pretty confusing, doesn't it? It's just rate. It's distance over time, but now I'm letting the time go to 0. Not a big deal. So that's the derivative. Bingo. We're done with the first question. And so now what do we see? Well, we see now that we come back to here, and the derivative, in fact, gives us the slope of the tangent line. Well, that's really cool. If you want to find a slope of a tangent line ever in life, you just take the derivative, and that gives you the slope of the tangent once you evaluate it at the point you want. Great. But for free, we answer the first question, because remember, the derivative also represents the instantaneous rate of change. So you want to find out how things are changing? No big deal. You take a derivative, plug in, and that will tell you how things are changing at that instant. Okay, great. So now we know all about how to graph these things, how to look at these things, the derivative, instantaneous velocity, boom, boom, boom. We got all out of the way. Now let's take a look at some applications. What can we do with this? Well, how would you take derivatives of complicated functions? Well, if you got a product, you need the product rule. Remember the product rule, don't memorize the formula, memorize the chant. First times the derivative of the second plus the second times the derivative of the first. So the derivative of a product is this. It's not the product of the derivatives. You got to use the product rule. We've got 5 minutes. This has been up here, folks. I got to move faster. What if you have a quotient? Well, then you use the quotient rule. And what's the quotient rule say? If you got a quotient, you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the quotient rule. That's what you use when you have a derivative of a quotient. Okay, great. No problem. Now, what about if you have a really complicated function? What if you got a function that looks like this? It's got insides. It's got guts right in there. So you've got something like this, and you want to take the derivative of that. What do? Well, you got to use the chain rule, folks. This is a thing that you can chain together. There's an inside. There's a blop right here. There's a whole big blop there. And then you've got an outside. So take the derivative of the outside. So the derivative of sine of blop is actually cosine of blop. So it's cosine of blop. And what's the blop? The blop is going to be 3x cubed plus 1. And then you multiply that by the derivative of the inside. And the derivative of that turns out to be just, let's see, 9x squared plus 0. And so there's the derivative using the chain rule. The idea is to peel off like an onion. Just peel off. Keep peeling off the outside until you get to the inside. Always remember, though, when you take the derivative, it's if you have sine of blop, the derivative is cosine of the blop. Don't put the derivative in there. Put the blop and multiply by the derivative of the inside. That's the key to the chain rule. Now we got the chain rule. Okay, but what about when you have functions that aren't functions? Like what if you have things that are relations? Like x squared plus y squared equals 1, like a circle. How do you differentiate that? How do you find dy dx there? Well, the answer is we use something called implicit differentiation. Implicit differentiation, how does that work? Well, you've got to remember that dy dx, that's an object. That's a noun. And d dx is a verb. It's a commandment. Take the derivative with respect to x. So you differentiate this with respect to x, and what do you see? Well, you see something that looks like this. What you do is you say, okay, I'll take d dx of x squared plus y squared equals 1. The derivative of x squared with respect to x is just 2x, not a big deal. The derivative of y squared, remember how I think about this? I think about this as clumping all this together. And I see this as a blop squared. So I actually use the chain rule, which we just developed. And the chain rule says the derivative of blop squared is 2 blop. And then I multiply that by the derivative of the blop, which is the derivative of y with respect to x. That's called dy dx, folks. The derivative of 1 is 0. And now you can actually solve this for dy dx by bringing this to the other side. That'd be a minus 2x. You divide by the 2y, and you see dy dx equals minus x over y. And there's the answer. So that's implicit differentiation. Just go right through and differentiate implicitly. When you have a relationship, you can still find the derivative. Great. We're making progress here, folks. We are cutting through this stuff. Well, now that you have derivatives, what can you do with that? Well, if you think about it as a velocity, you get instantaneous velocity. If you take the derivative of velocity, you actually get the change in velocity, which is acceleration. So we get acceleration now, we get velocity. Acceleration is just the second derivative of the position. So we can actually take derivatives upon derivatives upon derivatives, as many derivatives as you want. So it's great. We can do that. So higher order derivatives, no problem. What can you use these things for? Okay, we know it's true for velocity. We can use it for velocity. What else can we use it for? Well, it turns out you can use it for linear approximation. Suppose you got some wacko function. You got some wacko function like this, woo, and you actually want to figure out the value right here, and you don't know what that value is. But you know nearby there's a point that you can actually compute. So what do? You find the tangent line approximation because you remember that the tangent line closely emulates the activity of the function. The tangent line closely emulates the activity of what the function is doing, so they look the same there. So if you find the equation of the tangent line and then plug in the mysterious point, then you're all set, because you can approximate the value by plugging into the tangent line. So how would that look? Well, that's called linear approximation. Here's the formula, but don't bother memorizing it. Just think about it. What you've got to do is you've got to find the equation of the line that's tangent at the known point, which is x here in this case, and this is going to be x plus delta x. The known point plus a little teeny offset is going to be approximately equal to the derivative times the change in x times the function. Plus the function. So that's it. That's the whole thing right there. Linear approximation allows you to actually compute things. Computers actually work this way. Computers know calculus. Everyone knows calculus. You've got to know calculus.